Thank you, Sebastian. And thank you for still being here despite the hour and the day, Friday. Thanks, God. So this talk is about the robustness of causal discovery algorithms. And it was presented recently at ICMLCN conference in Barcelona. It is work that was primarily made by Tianzu Zhang and Davide Rinaldi, with my boss Armen Agasarian and myself in the role of like the person that makes the paper possible. But the work is mostly technically under Tianzu and Davide's responsibility. So you know and have heard about network function virtualization. It has been a kind of leading trend of kind of networking research and also productization of kind of network appliances. So what once used to be separate boxes with kind of custom hardware and software has been transformed into, let's say, some sort of mix and match of software processes that are virtualized or multiplexed over kind of common hardware like off-the-shelf. And this has, on one hand, simplified a lot the kind of construction of systems. You can just load a program and you have a BAM firewall, and another program is your IDS and filter for traffic. But then, of course, the problem is whenever you start having complex topologies of this sort of software, let's say, intermediary functions that are connected into complex topologies, you don't really know when things go wrong. And this is especially a problem for like high-speed kind of carrier-grade NAT and this sort of systems. Debugging in NFV is complex. You can have heuristics and logging. So basically, you can catch whether your processor is being overloaded by some function. But sometimes, like the issues that happen are very complex, and it's difficult to debug. And even machine learning algorithms are not enough to basically recognize that where is the original issue that is causing a cascading problem through the topology. So this work is basically a continuation of our long-standing research interest that has been part of our key links collaboration with Leonardo Linguaglossa here from Inference. So basically, previous work in the series, for those who may have seen it, is the work that was presented at Infocom last year about non-invasive performance prediction of network functions in software higher speed routers, where they were basically looking into hardware counters in order to infer what was going on at the level of traffic. So here we have taken a different, let's say, point of view, which is mostly the doing of our manager who is obsessed about causality. And well, I think that obsession was one of the best sources of inspiration. So basically, he wanted to see whether causal methods would be applicable to this sort of problem of NFV systems and understanding fault propagation. And therefore, causal methods have nice properties and allow counterfactual reasoning, which basically gives you a satisfactory and explainable kind of characterization of issues. And therefore, they are useful for identifying performance bottleneck, etc. So what we do in this paper, which I mean, is also a poster that you may have seen outside while browsing them, is we compare existing causal discovery algorithms in the literature. And to do so, we built or we reused the NFV testbed that we had for the previous paper that I mentioned to produce measurements and traces under controlled conditions so that we could basically compare the kind of causal discovery techniques in the literature applied to the specific case of NFV topologies and disruption scenarios. So causality, I will not delve too much into this because, well, we don't have a lot of time, but also because I'm not the best person to talk about this. It's not my, let's say, research area, but it is a field in which it has been provided a mathematical framework to understand and formalize the relationship about causal effect between things. Causality starts from a graph, which is usually a directed acyclic graph. Starts from variables, which may be endogenous, so basically variables which are under monitoring and control, and exogenous, which are basically outside of your system. That could be and functions that connect over the graph the various variables. And whatever you combine out of these things is called the structural causal model. And the purpose of causal discovery is to retrieve a structural causal model from observations. So basically, you have a system that you don't perturb, and you try to determine which variables are linked through functions in the graph. And with intervention, interventions could be like you take one variable and you kind of stick it to a single value, or you can alter the distribution of things so that it's different. So one is a hard intervention when you stick the value to a known value, and kind of alteration of distribution is a soft intervention. And causal discovery. To what do we apply it? Well, we did have this testbed already made, which we kind of further instrumented so that we could control the interventions on different GPUs, different CPUs, sorry. We pinned different processes to different CPUs so they would be isolated one from the other. So basically, we tried to have the kind of most control on what was going on. Basically, we extracted this data set from countless hours of Tianzu's time in cleaning up the data and making it so that we can assume about this data that causal sufficiency is there. So basically, there is no other hidden confounder that has been kind of involved in the generation of the data. And we have IID samples generated from this. So basically, there is no temporal dependencies. We don't have buffers or other things that could basically perturb over time. So basically, we have some sort of statistically, let's say, independent distribution of data without sort of convergence times, et cetera, et cetera. So, and we tried 3 different network topologies, which involve each 5 different functions combined in different ways. One is linear, others are acyclic graphs. And we collect 2,000 samples, and we do interventional, observational data sets, et cetera, et cetera. What we use to compare the performance of causal discovery algorithms is called the structural Hamming distance. It's a bit like a Hamming distance applied to graphs. So basically, if 2 graphs are equal, distance is 0. If you kind of say that edge exists when it doesn't, you take 1 point of penalty. If vice versa, say that an edge is not there, but it should be 1 point of penalty. And it's also sensitive to reversal of edge direction. So it is, I mean, it is very sensitive to basically deviation of what you find compared to what it should be. And the algorithms that we compare are 2 categories, like observationals, so PC, GS, Notiers, Golem, Grasp, and Lingam, and interventional, GS, DCDI. We introduce a sort of kind of shortcut, which, I mean, David, the inventor, was not very proud of, but he's never proud of anything because of like he's very critical of himself. It's basically a gross hack which uses a threshold on the Kurzweil-Leiber divergence on distribution of let's say points around let's say an average to tell which are the variables that tend to vary together in following an intervention. And so basically that's just a closure under set inclusion to define the graph without having too much care for like more complex causality definitions. So it is simple, it is our baseline, and we will compare it against other interventional methods in the slide, which is coming up. For the rest of the pointers to papers, so you can refer to the bibliography of our paper at the ICML-CN. So the 3 topologies are linear, DAG1 and DAG2, in which we arrange more or less the same functions. So first in a kind of linear chain, then in a sort of bifurcating configuration, and then in a configuration with 3 kind of ways that combine after in a bridge before the packets go out of our software router. And the kind of observation that we have, like a first sight, well, we also optimized using the linear topology, the IP parameters that all of these methods have. So basically, we try to see how generalizable across topologies the hyperparameters are. in the kind of cases of DAG topologies. And what we observe is that basically the observational methods are, let's say, not always performing well, except for GES, which actually recovers most of the time in all the configuration, the correct structure of the causal dependencies. So it is the kind of orange squares that are always going to zero. And it does so for a sensitivity level of the kind of disruption, which is very, let's say, good compared to other methods. So for disruptions which are larger at 30%, the GES always manages to recover the original correct graph. Other techniques which are observational kind of approach, but not quite the performance of GES, which is also one of the more complex methods. And sometimes they have a kind of constant, let's say, misbehaviors which consist to reverse the dependencies between cause and effect in certain links, such as the first one. So basically, sometimes they converge at 1 or 2 for Hamming distance, which is basically good enough, but not quite perfect. And other techniques which are observational are not very applicable, such as Notier, so which never really goes below 5 or 6 of Hamming distance. We can see that the generalizability is quite good. So even not having kind of tuned the threshold and hyperparameters of the methods, in the case of the DAGs, the behavior is very similar to the linear topology. And we also can observe that the interventional methods perform a little bit better than the average observational method, and transitive closure TCI, the method that we kind of introduced as a baseline, has a consistently good performance for a very kind of limited footprint in terms of complexity. So we then study a little bit, given a causal topology, how well causal RCA, which is a technique proposed in a paper that is pointed in the slide, how it works. So basically, we use our traces to find how successful we are to find a single anomaly or kind of to detect the distribution shifts. And we see that like around 47% accurate identifications of root causes are possible with a top 3 node kind of success rate of 67%. And for distribution shifts, which is kind of a more subtle way to detect anomalies, 50% accuracy in the identification of the real cause and 80% for the top 3. So we see by our results that once we have a good causal discovery through the techniques that we presented in the previous slide, then causal RCA is actually a kind of a possibility and could be actually useful to investigate network problems in NFV deployments. To conclude, this paper kind of shows a successful validation of causal discovery methods in NFV testbeds. We released the topologies that are kind of free to be downloaded. And we have established a simple technique as a baseline for future research in network causality analysis. So, of course, there are limitations. One is that this work applies to DAG topologies because it inherits all the limits of definition of causality. In networking, we have a lot of, let's say, procedure calls, which are basically going back and forth between a client and a server, et cetera. So this kind of chain of, let's say, acyclic dependencies is a sort of rare occurrence. And it would be nice to extend this work towards like support of this sort of, let's say, more realistic topologies that are found in our software network deployments. So thank you very much. Any questions?
Yeah. Okay. Thank you. So your graph, they're all directed graphs. Sometimes there are causality models in which you have, confounders that affect that are not direct influence, but essentially that have effect. So you get the graph, which is a superposition of an acyclic graph and a directed acyclic graph and a bidirected graph, and then it gets very hard to find where to do the interventions. Do you have that also in your applications?
I mean, the way like we do intervention is that basically we can subtract resources to CPU resources to any function. So we pick a function and say, you get half of the CPU now. So this is basically 50% disturbance. And basically, this has consequences on the other functions in the graph. And the graph being direct and acyclic by construction, the question is, can we discover which was the original function that was perturbed just by this?
Like minimal intervention program. So where to do a minimal, so where to to make a shift.
Here we do a sweep across all magnitude of interventions, and we see that for different techniques, there's different sensitivities. So basically, certain techniques require a very strong intervention before they actually catch the distribution, let's say, shift or the kind of change in basically causal behavior of the system. Others are, let's say, more sensitive, such as like GES, which is probably the best. And I think it's also the most complex technique that requires a lot of comparison and over model. So I'm not an expert in other techniques.
Okay.
But yeah.
Thank you.